Have you ever wondered? When your computer has only one CPU, how can it play music, browse the web, and download files in the background without slowing down? It doesn't even lag when playing videos. And what's even more magical is, decades ago, computers could only run one program at a time. How do today's operating systems make it seem like many tasks are running simultaneously? Don't worry, this video will take you deep into the topic. How is multitasking implemented? Why doesn't your computer lag anymore? I'm CodeBing, here to explain core computer technologies in plain language. If you're interested, don't forget to subscribe. First, let me ask you a question. You open a browser, listen to music, switch to a chat window, and then open a PDF. You might think these are happening at the same time, but in reality, your CPU can only execute one instruction at any given moment. So how does the operating system create the illusion of multiple tasks running simultaneously? The secret lies in its scheduling strategy. From the 1940s to the 1960s, early computers, such as those in the vacuum tube and transistor era, were limited by hardware technology, and operating systems had not yet taken shape. Users had to directly control the computer through physical wiring or punch cards, and only one task could run at a time. This was called single tasking mode. In single tasking mode, the user monopolized the entire system, and all resources, CPU, memory, etc. were fully occupied while a task was running. For example, in the 1950s, with the IBM 701, users had to wait for one program to finish completely before running the next. CPU utilization was extremely low, resources were wasted, and it was impossible to support multi-user or multi-program interaction. In the 1960s, as memory capacity increased and interrupt technology emerged, operating systems began introducing multiprogramming, the precursor to multitasking. The core idea was to keep multiple programs in memory simultaneously. When one program was idle, for example, waiting for I/O, the CPU would automatically switch to another ready program, avoiding idle time. A typical example was IBM's OS 360, released in 1964, which could load multiple jobs into memory. Multiprogramming achieved CPU and I/O parallelism for the first time. However, task switching relied on programs voluntarily yielding the CPU. If a program hogged the CPU, for example, due to an infinite loop, the entire system would freeze. Additionally, there was no interactivity. Tasks were executed in batch order, and users couldn't intervene in real time. In the late 60s and 70s, to support multiple users interacting simultaneously via terminals, time-sharing systems emerged. The core idea was to use time slicing to rapidly switch CPU tasks, making each user feel like they owned the system. MIT's CTSS was the first time-sharing system, supporting over 30 simultaneous users, and Unix further refined the time-sharing mechanism. Time-sharing systems introduced preemptive scheduling, using hardware clock interrupts to forcibly take CPU control from the current task and switch to the next. This was the first implementation of interactive multitasking, where users could input commands via terminals and receive quick feedback, laying the foundation for multitasking in later personal computers. From the 1980s to today, early personal computers had weak multitasking capabilities due to hardware limitations. DOS in the 1980s was a single tasking system that could only run one program at a time. In 1995, Windows 95 and Windows NT were the first to implement preemptive multitasking on PCs, combining multi-threading technology for significant efficiency gains. Modern operating systems, for example, Linux, macOS, Windows 10 and 11 represent the pinnacle of multitasking, supporting multi-process and multi-threaded operations, with scheduling algorithms adapted for diverse scenarios and leveraging multi-core CPUs for true parallelism. So-called multitasking isn't actually running tasks simultaneously but rapidly alternating between them so fast that you don't notice the switching. It's like a chef boiling water, cooking vegetables, and heating oil. They constantly switch between pots, but all dishes are eventually prepared. The essence of multitasking is rapid task switching, concurrency, or multi-core parallel execution, parallelism, and its implementation relies on four core mechanisms: processes and threads. The operating system must abstract tasks into manageable units, processes, or threads. A process is an independent program instance with its own memory space, file descriptors, and other resources. It's the basic unit of resource allocation. For example, opening a browser creates a process. A thread is an execution flow within a process, sharing the process's resources, memory, files, etc. It's the basic unit of CPU scheduling. For example, a browser might use one thread to load a web page and another to play a video. Threads are lighter weight than processes, with lower creation and switching overhead. Modern systems often use multi-threading for fine-grained task parallelism. Task lifecycle control. Each task state reflects its execution status, and the operating system uses this to decide whether to schedule it. Ready status. The task is prepared and waiting for CPU time. Running status. The task is currently executing on the CPU. Blocked status. The task is paused, waiting for resources, for example, I/O completion, and cannot execute. The operating system tracks tasks via a process control block, recording state, priority, and context, register values, program counter, etc. Deciding who runs next. Scheduling algorithms are the conductors of multitasking, balancing efficiency, CPU utilization, fairness, task response time, and scenario needs, for example, real-time requirements. Common algorithms include time-sliced round robin. Each ready task gets a fixed time slice, for example, 10 milliseconds. When the time expires, the task is switched out, ideal for interactive scenarios, for example, desktop systems. Priority scheduling. CPU time is allocated based on task importance. For example, real-time tasks have higher priority than background tasks, ensuring critical tasks aren't delayed. Multi-level feedback queue. Tasks are divided into priority queues. High-priority queues get shorter time slices for quick response, while low-priority queues get longer ones for background tasks. Linux's completely fair scheduler is an optimized version. Real-time scheduling ensures tasks meet deadlines, for example, drone control systems, using algorithms like earliest deadline first, the backstage work of task switching. When the OS decides to switch tasks, it performs a context switch, saves the current task's context, registers, program counter, etc. to its PCD, loads the target task's context from its PCD, switches memory mappings. If the task is a process, the page table must be updated. Context switching relies on hardware support, such as clock interrupts to trigger scheduling, privilege modes, kernel mode for switching, and register sets to store context. Switching overhead, typically a few microseconds, is a key factor in multitasking efficiency, so modern systems optimize algorithms, for example, reducing switch frequency to minimize it. However, multitasking can't be achieved with software alone. It requires hardware cooperation. Interrupt system. Clock interrupts and I/O interrupts act as triggers for switching. Memory management unit uses paging and segmentation to isolate process memory, preventing conflicts. Multi-core CPUs allow tasks to run in true parallelism on different cores, no longer relying on switching. Modern OSes assign tasks to idle cores for maximum utilization. So why don't today's computers lag? The key lies in optimized scheduling strategies. Operating systems use preemptive scheduling. Preemptive scheduling means the OS can forcibly interrupt the current task, even if it hasn't finished or yielded the CPU, and allocate CPU resources to a more urgent or higher priority task. This preemption is controlled by the OS kernel and doesn't rely on the task's cooperation. In simple terms, no single task can monopolize the CPU for too long. The system will force it to yield. Tasks are divided into different queues based on priority, wait time, etc., and the scheduler dynamically decides who gets to run next. For example, when you're downloading a file, background task, and editing a document, foreground task, simultaneously, even if the download is still running, the OS will periodically pause it to give the document task CPU time, ensuring real-time responsiveness while you type. This is preemptive scheduling in action. Preemptive scheduling relies on hardware and kernel mechanisms. Beyond preemptive scheduling, today's computers don't rely on just one CPU core. Multi-core processors allow each core to execute tasks independently. A multi-core processor integrates multiple independent computing cores on a single CPU chip. Each core acts as an independent CPU with its own arithmetic units, registers, and private cache, L1 and L2, while sharing some resources, for example, L3 cache, memory controller. This enables true simultaneous execution, not just rapid switching like single-core CPUs, greatly improving parallel task processing. Thread pooling allows thread reuse, thread management, model where a fixed number of threads are pre-created and reused to reduce the overhead of frequent thread creation, destruction, while controlling concurrency to avoid resource exhaustion. I/O operations, for example, file reads, network requests, are the slowest part of computing, milliseconds, far slower than CPU instructions at nanoseconds. Asynchronous I/O is a non-blocking I/O model that lets programs continue executing other tasks while waiting for I/O completion rather than blocking the thread. Multi-core processors, thread pooling, and async I/O don't work in isolation. They collaborate via hardware support, resource management, I/O optimization chain to solve efficiency problems for CPU-intensive and I/O-intensive tasks. These technologies combine to keep your computer running smoothly, even with dozens of programs open. That's all for this video. Today we covered why a CPU can only do one thing at a time, how the OS achieves multitasking via context switching and the scheduler, how preemptive scheduling and multi-core parallelism make task switching faster and more efficient, why modern computers don't lag. It's the result of combined OS and hardware efforts. If you found this video helpful, give it a thumbs up. Feel free to comment about any system lag scenarios you've encountered. I'll keep posting explanations of computer principles and programming knowledge. Remember to subscribe. See you in the next video.